Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be continuing our discussion of the laws and processes of thermodynamics. This time we're looking at different thermodynamic processes, kind of how they might be classified, and the kind of work that's done in each. So let's get into that a little bit. You'll recall at this point that we have described work for a thermodynamic system via the first law and via gas expansion. So our first law says that the change in internal energy should be the heat added less the work done by your system. And then we also have that the work done by the system with a constant pressure process is P delta V. So this is work with constant pressure. This assumption of constant pressure, by the way, is one possible thermodynamic process. It's called isobaric, which we'll get into later. More generally, we said that if we had a plot that shows on the one axis a volume and on the other axis a pressure, that if we want to find out the work done by the process in moving from one point to another along this curve, that the work done would be the area bounded by the curve between those 2 points. Put more formally, maybe we could call it the work done in going and taking a system or going from state A to state B via whatever process is actually described by this curve from A to B. Now note that there may be more than one possible process to get from A to B. For example, it may be that the process is instead isobaric, like so, and then same volume for the rest. And the word, by the way, for same volume is isochoric. So this kind of leads me to the basic thermodynamic processes that we might look at today. And each one of these processes that I'm going to describe is a constant something process, but the something changes from one process to the next. The word or the prefix iso in this case means constant or uniform, or you could think of it as same. So if we say isothermal, then we're saying same heat. If we say isobaric, that means same pressure. If we say, isothermal means same temperature. If we say isochoric, we mean same volume. And if we say adiabatic, we mean no heat has been added or removed. So that's sort of same heat. Now, in each of these processes, our first law of thermodynamics equation, this one here, and our work done, these two concepts here, may be slightly different. So let's think about this for a minute. What would isobaric imply? Well, we have constant pressure, and that is just the definition that we gave for work initially. This is under constant pressure. So we can kind of fill in already that in this case, work would look like P delta V. And it kind of deserves a little bit more description than that, but I'm going to be very brief because this is meant to be a short video lecture. If you have an isobaric process, here's my volume axis, here's my pressure axis. You're basically changing volume from one to the other, like so, with a constant pressure. So my final and initial pressure is the same. If I was to figure out how much work is being done, this area would be essentially the height of the rectangle, which is, we could call it P, times the width of the rectangle. That would be delta V. And so this ends up being work is P delta V. If you'd prefer, you could call this P naught or something like that, and this delta V AB for the volume between, or the change in volume between states A and B. But usually we just say P delta V in this case. So this one's kind of like the most straightforward process from the perspective of work being done. It has to be done at constant pressure, however. Okay. What about a constant volume process? Well, a constant volume process, isochoric, so isochoric is constant volume. What would that look like if I was going to try to plot it on the graph? Well, here's delta P, here's delta V. Maybe I start from here. Maybe this is point A. Point B has to be at the same volume as point A is. So point B would be down here somewhere. So I don't really have anything here to bound an area. I just kind of have this vertical line. And since delta V is 0, the implication of that is that the work done on the system, P times delta V, is also 0. So no work is being done on this system. What does that mean happens? That means that by the first law of thermodynamics, the change in energy for the system has to be equal to the amount of heat added or removed. So all we've done is just essentially change the temperature of our system by heating it or cooling it, or we've melted it, or we've vaporized it, or we've frozen it, or we've condensed it. You've basically just changed the internal energy state of your system. Okay, we come now to isothermal. In an isothermal process, the temperature remains the same throughout, so delta T is 0. The fact that delta T is 0 means that we would expect a curve more or less like this for our P versus delta V. How do we get that? Well, use the ideal gas law. So ideal gas law says that P times delta, or P times, V is equal to nRT, or if you prefer, K sub B capital N T. Now these are all constant. So isothermal, we're also assuming that there's no leaks in our system, but these are all constant. So that means that P is equal to a bunch of constants, KB in T over V. All right, so if I was going to plot P versus V, or delta V, I would get like a y equals 1 over x kind of graph. So this is, in other words, proportional to 1 over volume. So I again want to find what is the area under this curve in order to find the work done. Now you could do that by plotting the curve on graph paper, or plotting it in a computer and asking it to find the area under the curve, what have you. It turns out that there's an analytic formula for equations of this sort. Basically, we expect for the area of this thing to look like a natural log of the difference in volume. Put differently, the work done by the gas in this system should look like K sub B times N times T times the natural log of the ratio of the two volumes. So that would be final divided by initial volume. So that one is kind of a different looking equation than the other one that we had with the constant volume, or excuse me, with the constant pressure. This one was just a simple linear equation that says work is P times delta V, or in other words, is P times VB minus VA. So this one is linear because we had a constant pressure throughout. This one is nonlinear because the pressure depends upon the volume, And so when we go to find the area, we end up with this natural log of this ratio. And again, you can always just plot the thing and count boxes. If you're working on graph paper, it'll come out to very close to this result. So this is a credible result in approximation. Also worth noting about this system, if you have a constant temperature, then in actual principle, all three terms, Q, W, and delta U, may vary in this process. And again, even for temperature being constant, delta U can vary because obviously you can melt something, you can freeze something, that kind of thing. So there's latent heat. But also in a non-ideal gas, you end up with some additional effects for the internal temperature. However, if you are dealing only with an ideal gas, no phase changes, and it is an ideal gas, then the internal energy only depends upon the temperature. And so basically your work is going to be equal to your heat added. Last thing I should add here is that these processes, isothermal processes, are typically very slow because we need the system to remain in thermal equilibrium throughout. And in order for that to happen, any heat flow in and any heat flow out have to maintain a constant temperature. And so it has to be slow enough that the temperature isn't changing. This is in contrast, by the way, to the last process, which is the adiabatic process. Adiabatic process means that there is no heat transfer or no net heat transfer in the process. And so that means that this process typically needs to happen very quickly and preferably in a system that is well insulated. The equation that goes with this is that since delta U is Q minus W and Q is 0, it follows that delta U is just equal to W, is equal to negative W. As far as the graph for this is concerned, basically if we were to again plot pressure and volume, or pressure and delta volume on here, previously I plotted pressure and volume for the isothermal, which looked basically like this. So if I were to plot this as my isothermal process, this P is proportional to 1 over V. The adiabatic process would actually maybe be more equivalent to this. Essentially, you're going to have changes in delta U and in W, but your temperature is also going to end up different than what you had with isothermal. With isothermal, the temperature here and here is the same. For this same over here, your temperature ends up being somewhat lower because you're not adding any heat to the system, but you are doing work on or by the system. So in the isothermal process, temperature A and temperature B, or we could maybe label it B prime, should be equal to each other. You have the same temperature at the start and the end. But in the adiabatic process, so this is adiabatic, in your adiabatic process, you end up with a lower temperature after this process, at least for the process described on this graph, than what you started with. So TB is less than TA or TB prime. And that's again because you've added no heat to the system in this process. This is a process in which the gas is expanding and doing work. No heat has been done. Therefore, W itself is a positive number in both of these cases. But in this case, you also have a plus Q to keep the temperature higher. In this case, there is no plus Q, and so delta U has to be lower than what you started with. Therefore, you have a lower temperature than what you started with. The closest thing in real life to an adiabatic process that comes immediately to my mind is the compression stroke of an internal combustion engine. The process is usually rapid enough that there isn't time for there to be much heat flow into or out of the system, and so you have a compression of the gas within the within the cylinder, within the engine's cylinder, that is quick enough that the process is occurring with virtually zero change in heat, 0 Q. And so you're doing work on the gas, you're also heating the gas, and then that's as close to adiabatic as you're going to get. It's a very fast process. Are there other processes? Yes, but again, I don't really want to go into too much into the bushes on these. That is one example of an adiabatic process, so I think that should suffice for today's video. And that is all that I'm going to do in today's video. So, hopefully you learned from it. Thanks for watching.